Imagine a cosmic object with a gravitational pull so strong, not even light can escape its grasp. Welcome to the enigmatic world of black holes. These celestial entities are a riddle wrapped in a mystery, nestled in the great unknown of our universe. The concept of a black hole is as fascinating as it is mind-boggling. Picture a celestial body with a mass millions, even billions times heavier than our sun, all condensed into a single point in space. This point, known as a singularity, is so dense that it warps the fabric of space-time around it, creating a gravitational field of unfathomable strength. The boundary of this gravitational field is what we call the event horizon, a boundary from which nothing can return, not even light. This is why black holes appear as voids in space. But how can we measure something that seems immeasurable? Enter the Schwarzschild radius, a theoretical calculation that allows us to estimate the size of a black hole's event horizon based on its mass. It's named after Carl Schwarzschild, the physicist who first solved Albert Einstein's equations of general relativity for a point mass. According to the Schwarzschild radius, a black hole with a mass equal to our Sun would have an event horizon only about 3 kilometers across. That's smaller than the average city, but the reality of black holes is even more extreme. The largest known black hole, TON 618, is estimated to have a mass about 66 billion times that of our Sun. If we plug that into the Schwarzschild equation, the radius of the event horizon is about 195 billion kilometers, or about 1,300 times the distance from the Earth to the Sun. These numbers are almost too large to comprehend, but they paint a vivid picture of the unimaginable power and scale of black holes. These celestial giants are the ultimate embodiment of the old saying, out of sight, out of mind. Indeed, black holes are nature's most perfect hiding places, where the universe's secrets are tucked away. Black holes aren't born, they are the cataclysmic result of a dying star. Our celestial story starts with a star, not unlike our own sun, but significantly larger. In its prime, it's a fusion factory, converting hydrogen into helium, producing immense quantities of energy and balancing the inward pull of gravity. But as the star exhausts its nuclear fuel, this perfect equilibrium begins to falter. The star's core, now predominantly iron, can no longer sustain nuclear fusion. A sudden halt in the energy output causes an implosion, resulting in a shockwave that propels the outer layers of the star into space. This stellar explosion is what we call a supernova, an event so bright it can briefly outshine an entire galaxy. But what remains after this cosmic pyrotechnic display? Well, the fate of the remnants depends on the original mass of the star. If the remaining core is less than about 3 times the mass of our Sun, it collapses into a neutron star. These are incredibly dense objects, with a teaspoonful weighing as much as a mountain. However, if the dying star was significantly larger, say more than 20 times the mass of our Sun, the gravitational collapse would be unstoppable. The core would continue to shrink, condensing into a point of infinite density known as a singularity. This is the birth of a black hole. The black hole's gravity is so strong that nothing, not even light, can escape once it crosses the event horizon. Imagine an object so dense that if our Sun were to become a black hole, it would need to be compressed to a size of less than 6 kilometers across. So, from the fiery death of a massive star, through the dramatic explosion of a supernova, to the final inexorable collapse into a point of no return, a black hole is born. And so, from the remnants of a once vibrant star, a black hole emerges, shrouded in mystery and danger. At heart of a black hole lies a singularity, a point of infinite density. This might sound like a line from a science fiction novel, but it's a fact that has fascinated scientists for decades. A black hole is not just a hole. It's a region in space where matter has collapsed into an infinitesimally small, yet infinitely dense point. Firstly, let's explore the event horizon, the point of no return. Imagine a boundary so powerful that nothing, not even light, the fastest entity in the universe, can escape its gravitational pull. That's the event horizon for you. It's an invisible boundary, about 12 million kilometers in diameter for a black hole the mass of our Sun. Once crossed, there's no coming back. Now let's delve deeper into the black hole, past the event horizon. Here, we encounter the accretion disk. This is a swirling hotbed of gas, dust, and stellar debris, heated to millions of degrees, spiraling into the black hole like water down a drain. The accretion disk is the universe's ultimate recycling center, where old stars get a fiery send-off before their remnants are pulled into the abyss. But what lies at the center of a black hole? Welcome to the singularity, the heart of the beast. This is where the black hole's mass is concentrated into a single point of infinite density. It's a place where the laws of physics start acting weird. Our understanding of space and time, as Albert Einstein depicted in his theory of relativity, breaks down here. This singularity is shrouded in mystery, a mystery we are yet to fully comprehend. The numbers involved in the anatomy of a black hole are staggering. The gravitational pull, the heat of the accretion disk, the density of the singularity, these are numbers so large or so small that they boggle the human mind. Yet, it's these very numbers that drive our curiosity and our relentless pursuit to understand these cosmic beasts. In the heart of a black hole, the laws of physics as we know them cease to exist. But the exploration and the journey of understanding continue, bringing us closer to unraveling the secrets of the cosmos. Black holes are not just fascinating, they are terrifyingly powerful. Our journey into the abyss of black holes now takes us to their most alarming aspect, their potential dangers. The first danger we encounter is the bone-chilling phenomenon known as spaghettification. Imagine an astronaut, let's call him Bob, daring enough to venture into a black hole. As Bob approaches, the gravitational pull at his feet becomes vastly stronger than at his head. This differential pull stretches Bob much like a piece of spaghetti, hence the term spaghettification. As he's stretched thinner and thinner, Bob is simultaneously compressed from the sides. Now, you might wonder, how strong is this gravitational pull? Well, to give you a sense of just how immense it is, let's talk numbers. The gravitational pull of a black hole is measured in terms of its Schwarzschild radius, which is directly proportional to its mass. A black hole with the mass of our Sun would have a Schwarzschild radius of approximately 3 kilometers. This means that if you could compress the Sun down to a sphere with a radius of 3 kilometers, its escape velocity would exceed the speed of light, making it a black hole. But the dangers of black holes aren't limited to individual explorers like Bob. They extend to entire planetary systems. A black hole passing through a solar system could disrupt the orbits of planets, sending them hurtling into interstellar space or spiraling into their home star. The gravitational influence of a black hole is so great that it can even tear a star apart in a process known as stellar tidal disruption. And again, to comprehend the scale of this danger, let's think numbers. A star that strays within the tidal disruption radius of a supermassive black hole, which can be millions of kilometers, will be stretched into a stream of gas in a matter of hours, a cosmic spectacle as breathtaking as it is deadly. In the face of a black hole, even the mightiest planets are but mere playthings. So next time you gaze up at the night sky, remember the terrifying power lurking in the darkness, the black hole. Despite their destructive power, black holes may be essential to the fabric of our universe. They are not just cosmic vacuum cleaners sucking in everything within their event horizons. They might serve as cosmic architects, shaping galaxies and influencing star formation. Let's consider the theory that black holes might be the seeds of galaxies. The immense gravitational pull of a black hole could attract and hold together the billions of stars that make up a galaxy. The Milky Way, our home galaxy, has a supermassive black hole at its center, around which the entire galaxy rotates. This is not merely a local phenomenon. Nearly all large galaxies we've observed have a central black hole, suggesting a fundamental relationship. Another intriguing hypothesis involves wormholes. These are theoretical bridges through space-time, shortcuts that could potentially allow us to traverse astronomical distances in the blink of an eye. Some theories suggest that every black hole might contain a wormhole. If true, this would make black holes gateways to other parts of the universe, or perhaps to other universes entirely. The numbers involved are mind-boggling. If we imagine our universe as a two-dimensional plane, a wormhole would allow us to jump from one point to another, bypassing the billions of light years in between. That's a trip that at the speed of light would take billions of years. Black holes, while fearsome, may be the architects of our cosmic landscape. They are not mere monsters of the dark, but potential creators and connectors of galaxies, making the universe as we know it possible.